Hi, and welcome to this new tutorial series where we're going to use SpriteKit and SwiftUI to create a simple base builder game for the running on a Mac. And this is the first episode, so let's dive in. So our goal will be to create this simple game called Base Builder. We're going to use Swift and SpriteKit to really implement the basics, such as what would be the basis for a game like Prison Architect, RimWorld, or Academia School Simulator. And let me first show you what the eventual product will look like. So this is the game. Looks pretty simple. You can pause, you can zoom in, you can zoom out pretty far. You can pan around in the world. You can build, for instance, some additional flooring. You can create a wall. You can build the some walls. Oh, that's a bit much wall. You can do some wall here, and you can, for instance, install an object here. And the objects allow you to, for instance, change food into cooked meals. So this is really the basics that you can have in such a game where you build around your world. You add objects to it, and you have entities that have needs, and those needs can be met using the things you create. So that's it what we have for now. So let's get back. So this is what we're going to be building, and the hero in this series will be the job system. So this is our primary relationship. We have a player, that's you or me, that can queue up jobs, and those jobs are performed by entities, and those jobs in some way change the world. Jobs could be to change a tile, to install an object, to improve a need. It could be lots of things. And the world is a simple tile-based world. It has the entities in it. It has a list of jobs. It has items in it and some stuff more. In the previous series, we focused on using GameplayKit. This time we'll focus on the job system. So our intent is to make a really reusable job system that is pretty extensible going forward, and can be added to as much as you like. To make it a bit more interesting and more complex, there's a secondary relationship, and that's based on requirements. So a job to, for instance, change a tile might require some items. And the idea is that if you don't have the items with you, you might spawn a job that fetches the items somewhere else. So a top-level job like changing a tile in the world can then spawn sub-jobs to really meet those. Our visual representation is going to be pretty simple. So there's a bit more SpriteKit here than in the last one, which was really more of a terminal-based game. There is some interesting integration of SwiftUI for the actual user interface. We'll use assets from the Kenny. He has a great roguelike pack and a roguelike indoor pack. But I created sliced sprites for you in this zip file, so that will speed you along. Make sure you don't have to cut out all the sprites manually yourself. Now, the tutorial structure will be somewhat like this. So it's a bit difficult to predict right now how many episodes this is going to take, but I assume at least 8 to cover all these topics, perhaps some more, because some things do really take quite some time, especially when we start diving into user interface work. And today we'll focus on implementing the primary relationship, and that means implementing the primary data structures, the world, including tiles, entities, and jobs. We'll also create a couple of supporting data structures, the vector, which we also used in the last game mini stealth, and we'll add to that a queue and a stack. We'll use a queue for the jobs in the world. So basically, when you create a job, it gets added to the queue, and entities can take jobs from the queue, and the oldest ones are picked up first. The entities themselves will have a stack of jobs, which we can use to add subjobs to it. It will make a lot more sense when we start diving into it. And we'll write tests to validate the primary relationship. So we'll be using the Xcode test framework to write some integration tests to see that this is working. And there will not be any real graphic work today. So let's get started. So let's fire up Xcode and create a new project. And let's see, then I need to probably close this screen. Yes, so here's Xcode. So we're going to create a macOS game. We will call it Base Builder Tutorial. We'll include tests. We don't need gameplay kit. We'll use SpriteKit as the game technology. We'll use Swift as the language. That's it. And we'll find a nice place to put this. So we'll put it here. We'll create a repository for source coding, and that's it. So this should be good right now. And now we have the basic empty Swift SpriteKit project. There's always a lot of stuff here that we don't need, so we're going to get rid of the standard scenes. We're going to get, in the view controller, get rid of this stuff because our scene will not be loaded, but we'll simply have a scene that is the game scene. We'll use a different aspect, scale mode. Let's see, that's resize fill. So that way we can have a window that's resizable. We'll present the scene, and we'll keep all the other stuff as is. Then we'll go to the game scene, and this also has some stuff we don't need. So we're not going to use gameplay kit. We don't need all this stuff about spinning nodes. We can keep the events, and we can keep this key down one. And let's see if this compiles. Then at least we should get ourselves an empty window. Not very exciting, but at least we have these basics done. That is all the graphics work we'll be going to do today. So let's start working on our game, and I'll start by creating a group called model. And this model needs to have, well, let's start with the tiles, because those are probably the simplest data structure. We have tile.swift, and this will simply be an enum tile, and we'll have a couple of cases. So we'll have a void case that's really an empty tile. We'll have a case called floor. We have a case called wall, and we have a case called grass. And we'll use string as the raw type, so we can easily translate between the string values and these case values here. So that's, we will add more stuff to the tile later on, but this is enough for now. Then let's look at our entities. So the entity will be like the workers in the game, or the humans, or the animals, or whatever you would like. So we'll have an entity at Swift, and this will be a class because we want to be able to reference a specific entity quite easily. And let's see, this one should at least have a name, and it will have a position. And for a position, I want to use the vector type we used in the last game, which means that we need to somehow bring this in. So I'll make another group for util stuff. And this one will have a new file called vector. And this will be quite a simple structure. We will be reusing a lot from the last one, but I'll just type them in quickly. So we have an X and a Y value. This creates automatically an initializer. That should be no. This should be a struct. It's sick. I'm in a different file now. So we have name position. We have a vector here. Okay. We'll have a simple convenience variable to quickly get a zero vector out of it. So this one just returns zero vector. And we need at least a bit of arithmetic, so we should be able to do something like add them together and right hand side, and this should return another vector, and this is just a vector that gets you the left hand side of x and the left hand side of y, but adding the right hand side of y. And something similar, which is also useful, is to do the subtraction. And I think this should be enough for now. So now at least our entity will have a name and a position, and it requires an initializer. So let's see. So we'll create an initializer and with a name and a position. Self position is a position. Okay. So this is at least a start. Now we want our entities to be able to work on jobs. And as we introduced, the entities will have a stack of jobs, and they will work from the top one all the way down to the bottom one, and they can add to them as needed to fulfill jobs. So to do that, we need a stack data structure, and we'll implement a very simple one in Swift using some generic. So we'll create a structure of type stack, and this will be a generic that can take another type. And that's what the stack will store, and will conform to the collection protocol. This way we can sort of use them just like arrays and dictionaries and so on. So we need a couple of things. So first off, we need some way of storing data. So what we'll do is we'll create a private variable called storage, and this will just be an array of type, of the specific type that's being passed in. Then we need two functions to work as a stack, and the first one is we need to be able to push stuff on the stack, so basically add something to the top. And this will be a mutating function that simply takes an element of type t and adds it to the storage. And we also need one to pop stuff from the stack, and this might return an object of type of the type it stores, but it's an optional because perhaps the stack is empty, and then popping shouldn't return anything. So to pop, we'll just say regard storage.count is larger than 0, else we'll return nil. We need to do that because if you do storage.remove last, it assumes that you already checked that the storage array is not empty. Now you'll notice that we get an error that we don't yet conform to the collection protocol, and that's because we need to implement a couple of additional functions and variables. So the first one is we'll need to implement a function that creates an index of int. Basically, this helps you get the next index, and we can fortunately just use the one that's part of storage, so that's one. And we also need to subscript, so we should be able to get a specific part of our stack. This one I just copied somewhere else, so it's not something I typically use. I think we need a couple more. So I think we need to have a first index and a last index. So what we need is a variable start index, type int, and this will be the storage.start index. And we need a variable of type end index. And the final function I want to implement is a peek function to simply look at the top, the top object of the stack. We'll create a function called peek. This will create an optional of the type of data we're storing, and this will just return the last part, or the last one. So now we have a stack structure, which means we can have an jobs, a stack of jobs. Now we haven't defined yet what a job is, so let's do that right now. So we have our entities. Now we'll take the next big data structure, and that's the job. So we'll create a new one that's called a job, and a job will have a couple of things in it. So the first thing a job should have, it should have a goal or an intent. We'll call this the job goal, and we'll use an enum to describe all the job goals we understand in this case. In this game, so we'll create an enum called job goal, and for now we'll add only one case, change style, and we'll use the associated values option of enums in Swift to tell it also what type of tile needs to be changed. So now we have a job that has a goal. Well, we can change tiles and we can add more cases later for different types of jobs. The job should have a target position, so it needs to be done somewhere. And it will have a build time, so not all jobs will be will take the same amount of time. And it will be a variable because we want to be able to decrease this, because we will be able to basically say how much time it takes when we create a job, and then each time we work on it, we want to reduce it by a certain value until it's done. Then we need an initializer. Autocomplete now gives us quite a useful one, but I want to have a default build time of 1. So this will help us get a job, and now our entities should no longer complain. Finally, I want to make a start with our world. And then we can start implementing some actual behavior. So we'll have a world. This will also be a class, and I don't want people inheriting for this one, so I'll mark it final. So it will at least have a set of tiles. And these tiles will describe a world as a dictionary from a vector and a tile. This is probably not the fastest data structure to do this, but at least it's pretty easy to use. It complains that vector does not conform to hashable and therefore cannot be used as a key for the dictionary. No problem. We'll go to vector, add an extension, and we'll say it should conform to hashable, and Swift will take care of the rest. So we have a world, we have tiles. We also will have a set of entities in our world, and this will just be an array of entities. And we want to have a queue of jobs, basically a queue where we as a player can add jobs to. We'll have a variable called jobs, and this one will be a queue. And we haven't defined a queue yet, but it's quite similar to the stack. The only difference is that a queue works slightly different in that we don't push or pop, but we will be enqueuing and dequeuing items. So let's have a look. So we have a queue. Again, this is we'll use generic so we can store different types of items. We'll create a private variable that is the storage for backend for this data structure. And then we will implement the primary function. We have a mutating function called enqueue, and this will take an element, and what we'll do is we'll store it at the end of the array. So this is sort of similar to the pushing of the stack. However, the dequeue function is slightly different, because this one takes the first item. So we have a dequeue function that might return, it returns an optional of the stored type, because perhaps the queue is empty and then you can't return something. What we'll do is we'll make sure that we have more than one entries. Otherwise we'll return nil, and if we have more than one entries, what we'll do is we'll return the first one. So last time we used remove last, now we'll do remove first. And that's the basic difference between a stack and a queue. Again, we need to add stuff to it to make it act to conform to collection. So what we'll do is we again need to start in the end index. This is all more or less the same. And we need to index and the subscript functions. We'll add these as well. And this should now allow us in our world to create a queue of type job. And create our world. So these are all initialized values, so that we don't need a specific initializer. We now have the data structures that we need to store the most important data in the world, but there's no behavior yet. To add behavior to it, what we will do is we'll create an update function for the world, and this one will go through each entity and call an entity update function, where we will update the entity, and let's add that function right now. So we need a function here called funcUpdate in a world. And we can describe our primary behavior in this function. So what we'll do is we'll see if our jobs is empty. We'll if we don't have any jobs queued in a stack, what we'll try and do is get a job from the world. So we'll see if we can get a new job from the world jobs.dq. And this will also remove it from the world job. So this way an entity can claim a job. If this is correct, we'll do a jobs and push the new job. And if everything is going well, we should now have a new job. Else, if we already had a job, we'll just work on the job in the world. And this is a function we need to write. So we'll create a private function called work on job in world. And we'll continue working on this in a bit. One thing I want to do is I want to be able to get some logging data out of this one. So what I'll do is I'll use the OS log framework that's standard in AppKit and in iOS. We'll import OS log, and then we can create a logger, and we will call it this is typically what you call the application in the project settings. So the bundle ID, typically you use the bundle ID there. And as a category, you can just say Builder tutorial. And we'll look into how we can read those later on. But this way we have a logger that we can reuse. And we need to put it not as part of this class, but this will just be a free global variable, so we can log this way. Then when we go into here in our entity, for instance, what we can do is we can go to say, okay, we have a logger, and we'll info a message. We'll call it entity with our name picked a job. I'll call this new job. This will now complain because a new job can't be converted to a string, at least not in the way that the logger accepts. We can fix this if we create an extension for job to have it conform to custom string converter. And this is what we'll do. We'll create a description for computed property that says job goal at, and then a target position. And we can also create a debug description to get even more data out of it. So we could say something like job goal at target position, build time remaining, build time. Okay, now we should be able to log. And it requires self here. Okay. So we will get a message if the entity picked up a job. Now let's move on. So what if we have a job? Then we will work on a job, and we'll do so first by making sure that we have a current job available, and that will be jobs getting the top job. Else And this should never happen because we already checked here that it's not empty, but so that therefore I feel confident crashing here in a very loud way to make sure that if this happens, it immediately calls attention to it. Let's use the logger again and create a debug message saying entity self.name works on job current job. For now, what we'll do is we'll just set our position to the current job target position. So we'll teleport there. We'll implement actual moving to a location at a later time. And what we'll do is we'll take the remaining build time and reduce it by 1. Now, if the current job build time is less than or equal to 0, then we will complete the job. In the world, we'll implement that function in a bit. Otherwise, we are not done yet. What we'll do is we'll push the current job back on the stack. But this time we will push the updated version to the stack, meaning the build time is a bit lower than last time. And next time we do an update, perhaps it's done then. So let's implement the complete job function. Private func complete job. We'll take current job and complete it in the world. And then here we need to check what the job is actually intending to do. So we'll switch on the job call. There's only one case currently, and that's changing a tile. So we'll extract the associated value here. And all we'll do is we'll do world. And I think we we made tiles private set, so I can't just immediately change it. But what we can do is create a function called set tile at a position, and then make sure that the position is set to the new tile value. And then we can go to an entity, we'll do world set tile. This will be the current job started position, and the tile will be the tile we got from the job call. And then we can again log this data as entity finished job current job. Okay, so there was a lot of code, and we don't have anything to show for it. So I think we should be able to build this project now. We can also run it, but it's going to do, well, more or less nothing. To see that this is actually doing what we intend to do, we're going to create some tests. So we'll start by creating some tests to test this entity job work, and what we'll do is we'll go to the base builder tutorial test. We'll add a new file, and this file will be of a unit test case file, and we'll call this entity test. We'll add it to the product, and we can get rid of all this stuff, and we'll create our first test. So we'll create a function called test, and we need to start with test as a name, and we'll do a test job updates lower build time. So basically what we want to test is when the entity updates, the build time gets lowered. So we can see that actually work is being done. So we create an entity, and we need to import our project as a testable. So we get access to our entity class. We'll give it a name, example entity, and it can just be on the 0 location. We'll create a job. We'll change the tile to a floor, no problem. At position 0 as well. And the build time we will set to 2. Then we'll take an entity, we'll take the jobs, and we'll push this job on the stack. We also need world. And then we can start performing assertions to check whether values are as expected. So right now we expect the jobs count for our entity to be 1. And we expect the remaining time the job needs to run to be 2. This returns an optional, so I'll give it a value of 0 as a default. This way you always get an error if for some reason this returns nothing, but that shouldn't happen because we already checked that we have at least 1 in the previous assertion. Then we'll update the entity in the world and we will retest. And now the jobs count should still be 1, but the build time should go from 2 to 1 because we've worked on it for the first time. And then we will again do an update, and this time the job should finish, so there shouldn't be any jobs anymore in the entity's job stack. So that's our first test. This simply tests if working on jobs at least progresses them. It's also nice to see if we can actually get a job to change our world in a meaningful way. So let's create a test called job creates a tile, changes a tile. That's in this case more or less the same. So we'll create a world and we will make sure that our world tiles.count is 0 because it's an empty world. Then we will create a job again to change the tile to a floor. We'll have a target position of 0 and we'll have a build time of 2. We'll have an entity. We can call an example builder. It will also be at 0. And this entity will be working on this new job. So we'll push this job to the top of the stack. Then we'll make sure that the world tiles in place 0 is still a void. Now because this is a dictionary, this will return an optional, so we'll give it a default value also a void because we assume that if no tile is defined, it will always be void. Then we will have our entity and update it in the world. And now still world tiles 0 should still be void because this job takes 2 updates to complete, and this is only the first update, so the world should not have changed yet. Let's update it again. Now this tile should be a floor, and the jobs in the entity should be 0. Now let's see. So I think we should be able to run these tests. And these tests pass. I want to write one final test before we wrap up. And this will be a test for our world. So we'll create a new file. It will again be a unit test case class, and we will call it world tests. Get rid of all this stuff. We call a func test entity takes a job from the queue. Basically, we want to test that an entity is able to take jobs from the queue, the world's jobs queue. So we'll create a new world, and we'll create a job. And I always forget to import the actual product. So we have, we'll again change it to a floor, same position and same build time. Then we'll create an example entity. And it will have a name called test entities. And the position will be on 0. Our world entities will be just this entity. And the world jobs will enqueue this job. Now, if everything is going okay, our world jobs count should now be 1. And the entity jobs.count should be 0. Then we'll update world, and this should then also update all the entities in the world. We'll assert that now the world jobs count is 0 and the entity and jobs.count is 1. Let's run this test. So this test exceeds as well, so you can run the tests from this panel in Xcode, and we can see them all passing so far. I think this is enough for now, because we validated a primary relationship we defined here between entities, jobs, and the world. And the only way we queued up now is programmatically through the tests, but in the end we'll use the user interface to do so. So thanks for watching so far. It doesn't look like much because there isn't much on the screen yet, but there's actually a lot of this is a lot of groundwork that we needed to cover. Next time, we'll look at requirements and subjobs, and that's where the job system really starts shining, because then we can have a requirement such as that an entity needs to be on a specific location to perform a job. The job notices that it's not there yet. It spawns a second job to first go to the new location and then perform the job. So then you can sort of build jobs from jobs in a sort of a recursive way. It's pretty cool. Thanks for now. The source code will be published on my GitHub, so I'll add it to the description and link below. Thanks so far and have a very good day. Bye.